Welcome back. So, there are few things which are left out in the fluvial landscape part, and so this is the portion which last time we discussed about the first order and second order drainage and all that. So, in this one is a very basic part which usually has been used to understand the drainage density, and that can also help us in knowing the subsurface material or the lithology which is present in the area. So, drainage density is calculated or obtained in a very simple way with the expression here, which is, or the equation which is given here. So, d and sum of the length of the channel per unit area by area. So, you get this information by kilometer per square kilometer. So, usually the overall, like if you take this, if this is the basin area, and whatever the drainage you have, the length of the drainage are been added and the area has been taken into consideration. So, that will give you, so overall length of all the drainages or the streams divided by the area of the basin. So, this is one exercise which can be done, and if time permits we will try to do that. Other than that, as I told that if you consider the drainage density, that also helps in understanding that what exactly the material is existing subsurface, and the drainage density will depend upon the property of the material, and that is exactly the permeable. If it is permeability is high or the permeability is low, that depend of, or we can say the material is porous, then we will have mostly the drainage density will be low. So, that also helps in some certain sense to understand the overall landscape, and to some extent hydrologists and geomorphologists, they usually use this to understand the landscape dissection and runoff potential. Runoff potential is again that parameter can be helpful in the flood analysis and all that. So, on highly permeable landscape with small potential for runoff, okay, so drainage density are sometime less than, this has been observed that it is less than 1 kilometer by 1 square kilometer. So, that means the whatever the rainfall is falling on the surface, or the precipitation or the water, you can say it is completely seeped very quickly, and that will not allow the drainage to form. Hence, we will see less amount of drainage, or density will be less in that. On highly dissected surface, the drainage density of over 500 kilometer per square kilometer are often reported. Okay. Closer investigations of the processes responsible for drainage density variation have discovered that the number of factors collectively influence the drainage density or the stream density, and that what I briefly discussed a few seconds back. Okay. So, these factors are mainly of course the climate, then the topography, that means you are talking about the slope. Climate again you indicate it indicates the amount of precipitation you will have. Soil infiltration capability, that what I was talking about, that it is porous. If it is the material is porous, you will not be able to see much of the drainage developed on that area. But if it is less porous, or you can say the permeability is very low, then you will be able to see that the drainage is more over there. Vegetation also plays an important role, and of course, what we are talking in total is the geology or the lithology of the area. Okay. If the infiltration dominates over runoff, tend to have lower drainage density. So, this is mostly seen in if you take the sandstone, if you are having, okay, or if you are having the sandy areas, there you will be able to see that the density is quite low as compared to the other region. Okay. So, for example, this is just a sketch which shows that the sandy hills, okay, the area which is occupied by the sandy hills over here is having very low density. Okay. That is drainage density you are talking about. Now, based on this, again to make interpretation easier, there are further brief, I would say, that classification or the sub classification has been done, which helps in again identifying that what is the material available now. So, this example what we are looking at shows that the sand promotes infiltration, eventually result into low drainage density. So, that also can be taken as one of the interpretation. This is what I was talking about, the drainage texture. Actually, we take the drainage texture is defined as relative spacing of drainage lines, okay, commonly termed as coarser, medium and fine. So, coarser, if you take, then what it shows is that it is you have low drainage density, develops on mainly hard rock resistant rocks or over a highly permeable material. Okay. So, you will not find much of these streams if you because we are talking about the low drainage density, hence can be classified as in showing as a low drainage density, which can be termed as your coarse drainage texture. Medium, moderate density again develops on hard with moderate permeability. So, this parameter is playing an important role, that is mainly the permeability. Then comes to this is medium, then comes to fine, if you say they are closely spaced. Okay. So, in this case, if you say the closely spaced, this was moderate density. Okay. So, if you say closely spaced, then it will have a very like high drainage density in this case. Okay. So, mostly it develops on a loose or poorly cemented rocks or material like you are having clay, silt having low permeability. So, if you are having low permeabilities, then this will allow the water, it will not allow the water to seep down or infiltrate very quickly. That will result into more streams development, and that one of the example for that is your shale. So, shale is again sedimentary rock, argillaceous sedimentary rock. So, you will find more number of streams here. So, drainage density will be higher here, and we can classify this as a fine texture because the streams are closely spaced. Okay. Similarly, different rocks, like this is an igneous rock here and this is your intrusive igneous rocks, this is sedimentary rock, sandstone. So, they will have different drainage density and can be classified as an as we have discussed here. So, this will be coarse, this will be, you can say this is also coarse to medium or medium to coarse, you can say this one. So, you are having medium to coarse, this one is you can say medium, and this one is your fine. So, this you can classify accordingly. Okay. Now, we will move to another topic which is also again we are trying to put it with the drainage part. So, that we will see in the next one. So, this is another of course, I would say not a new topic, but it is aligned with the what we have been talking based on the landscape, how we can identify the influence of tectonic, that is ongoing deformation on that. So, we term this as in this branch is a sub branch of the geology or geomorphology, we can say tectonic geomorphology, okay, where the tectonic influence is more than your climatic perturbations. Okay. So, tectonic geomorphology is the study of landforms that are resulted from tectonic processes. Okay. So, we usually look at the right from the plate tectonics, two continents are colliding as in case of the Indian plate and the Eurasian plate, or the two continents, or we can say the oceanic plate or continental plate, either it is subducting or two continental plate is colliding. So, Based on this ongoing deformation, we can also see the signatures preserved on the landscape. So, that can be identified through morphological analysis in tectonic geomorphology. TG is we have just acronym of that we have put is tectonic geomorphology, mainly refers to measurements of the topographic expressions from topo maps or satellite data. So, again this can be done sitting in the lab or on your PC. You can have high resolution satellite data, and then you can, or you can even use higher scale of topographic maps, like for example 1:25,000, and that you can extract the information such like what we are showing here is the mountain front sinuosity and facet percentage. Okay. So, mountain front sinuosity, how much it is sinus. So, sinuosity basically the word comes from the river sinuosity also. It is here how it has been meandering or how it has been curved in a sense. Okay. So, usually we understand that if you are having, like for example, if you are having this mountain, and then you are having this. So, this will be your mountain front. Okay. Now, this I am showing in section, that is cross section, but if you look at in the plan view, then if you have this mountain front. So, this is like alluvial plain, and this is the hills, or you can say mountains over here. So, then if this is very straight, this contact between the mountains is, again we say the geomorphic contact. So, if you are having this very straight line, then we say that this is very active. But suppose it is having like dissected, okay, or sinus, okay, then we say that this has been eroded. So, this will be eroded by the streams flowing across it. So, that what we try to look at the mountain front sinuosity, and of course, again this also get associated with the facets. Okay. So, we say these are all triangular facets here. So, that we will discuss in coming slides. Okay. Then we also look at the longitudinal profiles of the stream, because if you take the longitudinal profiles, then you are having, you basically try to incorporate the distance along the x axis, and y axis you usually take the elevation. So, river profile usually looks something like this, okay, where it goes and meet the ocean or any major trunk stream, okay, or if it is a trunk stream, then it goes and meet the water body, either it is ocean or some water lake or pond or whatever it is. Okay. But usually we take this typical river profile. If there is some change in the river profile, for example, if the profile is seen like this, then this portion will have different landforms, and we try to understand that whether there is an sort of an upwarp in the profile, or suppose you see something like this. Okay, and this is what. So, we suggest this as an sort of an area of subsidence, and this will be the area of, like we can say this is your uplift. So, we try to understand that what exactly is going to happen in this area, because mostly the stream or the channel will try to keep itself in equilibrium. So, it will try to put itself in equilibrium. So, it here to get to this profile, then it will aggrade here, there will be deposition, but here to put itself in this area, then it will sort of degrade. So, there will be an erosion here. So, you will see a deposition here, and in this area you will see erosion, because the river will try to keep itself in equilibrium. So, longitudinal profiles are also important when we are trying to understand that how the tectonic influence is there on that. Okay. Then another point is the valley width to valley height ratio. Okay. Now, valley width to valley height ratio, again, if you are taking, if you have a stream flowing like this, and if you take this cross section, for example, AB, then what you see usually is that stream is having the profile like this. So, this is the A point and this is B point you are having. So, depending on this ratio, how, so sometime you will see that the valley is quite steep. Okay. So, that also suggests that there is some influence of tectonics. Okay. If you are looking at the wider valleys like this, okay, then for since long, like since a longer time, this area is not been affected by that. So, okay. So, V shaped valleys and U shaped valleys, of course, one can say that U shaped valleys are very common in glacial terrain, mostly in the alluvial plains, or maybe at least in the hilly areas where the glacial influence is not much. If you are coming across such signatures, that also helps, because this whole process is involved in what we call incision, and that is your erosion. So, this is again an important factor which we can look at. Okay. And pseudo hypsometric integral, this also we will discuss at the later stage, and you can use this parameters to identify the tectonic influence on the landscape. Then we will talk about the stream gradient index. So, this point, like this parameter, fifth one and second one, can be used together side by side. Okay. That can help you in understanding the overall tectonic influence. So, for example, this is in topographic maps of the foothills of Himalayas. It is in Punjab Himalayas, I would say, or the probably this is close to the Punjab region. Now, as I told that you can use the topographic maps as well as the high resolution satellite data to identify or to work on the your mountain front sinuosity, one, and second is your facets. Okay. So, we will see what exactly how we are defining the mountain front sinuosity, and how we are talking about what is the percentage of facet percentage. So, mostly if you look at this front, okay, so this is here, like if you look at this contour of 20 meter over here, then if I draw this one here, this goes like this. Okay. So, at some extent what I see is, or maybe you can take the inner one, that would be, because this is getting into the plane, but this if you take, then you have, I will just quickly draw this one here. So, then this is getting dissected here. Now, this is the same one, maybe inner one we can take, goes like this. So, this is, I am just roughly putting, but when you come here, this is again slightly dissected, but as soon as you get into this one, it is becoming almost straight. Okay. So, this portion is having higher sinuosity, and this is having low sinuosity. Now, so what exactly it is indicating, even if you take this one here, it is quite straight. Okay. So, this portion we studied in detail with the help of high resolution satellite photograph, and also we did a detailed field. So, what we found was that this area is, of course, this is a sub Himalayas you are having, and this is your Indo-Gangetic plain. IGP is your Indo-Gangetic plain, and we very well understand that this contact, what you see is the plate boundary. Okay. Now, within this, there is along the plate boundary, the contact, and the fault which runs here is been termed as Himalayan frontal thrust. So, this is a thrust fault. So, that we know that this is one of the most seismically active plate boundary in the world, but at the same time, if you want to identify that which area of this boundary, okay, or the fault line is more active as compared to the other one. Okay. So, in the nearby region, so that also helps in by you can do it by this two parameters. Okay. So, this more or less straight line, not much dissected, whereas this one is dissected one. This shows the presence of the signature on the surface, that is your active fault. That does not mean that the faulting will not occur over here, but this gives a very prominent example, and this example if you see is over here. Okay. So, this is the front which we are talking about exactly in this area. Okay. And if I carefully try to locate this, then this stream is this one here. Okay. And you are having this one is probably you are flowing through this one. Okay. This stream. So, the landform which you see here is, you can mark somewhere over like this. Okay. And this is the uplifted terrace. So, we can also like demarcate easily. So, this whole area is shown here, and this stream what you see is coming like this and then flowing down is this one. Okay. So, this is the area which has been marked in this portion. Now, as I told that if you have to differentiate between the active and inactive front, then this is the best photograph which you can look at. Okay. So, this one is inactive front, where we see a diffuse boundary between the alluvial plain and the hills, whereas this one is showing very sharp contact. Okay. Very sharp contact. So, this is active front, and another part which I was talking about, the mountain fronts. Okay. Mountain fronts and the triangular facets. Okay. So, we usually call them as a triangular facet. So, if you carefully look at this one, they are producing or showing some sort of an shape which resembles to triangles. Okay. So, these are typical facets. Okay. And we call this as a triangular facets. So, depending on the percentage of facets also, you can judge whether this area is active or inactive or moderately active, and so. So, how this triangular facets are been developed is basically based on the, or it will be resulted based on the your erosion of the stream which are flowing on the either side from the hills debouching into the plain areas. So, this image is from the foothill zones of Punjab, Chandigarh. This town is here, Chandigarh, and this is your front. So, if you immediately look at what we have discussed in the last slide, okay, then you can easily make out that this front is quite active, and this shows that there is the fault which exists here, and this portion we have named as Chandigarh fault. Of course, it is a part of Himalayan frontal thrust. So, that you can we can see here. So, it shows very clear demarcation or geomorphic boundary between the sub-Himalayas and the Indo-Gangetic plain. Another one here you can see. So, basically we try to use the remote sensing data, and along with that, of course, at few locations you need to do the field and try to confirm what you see on the satellite data. So, this is the area, the topographic map which we have prepared, not topographic map, we can say the From the satellite data, we have prepared this as an geomorphic map. Okay. And since we have incorporated not only the landforms in this, these are all landforms which have been marked with the pink, yellow and different colors. So, these are all terraces we are having marked here, alluvial fan surfaces as well as the terraces. Along with that, we have also marked with the red line you see is the faults which are displaced. So, if you see this portion here, this one is exactly this area. Okay. And this line which I am putting as bold is this one. Okay. So, you have instead just saying this as an geomorphic map, we say this as an tectono-geomorphic map, because we have included here the tectonic features also. Similarly, this one here, what we see is that there is an echelon faults which are running, okay, and then we have a back tilting over here at Mandhala, which is again a part of the Punjab Himalayas we are having. Okay. So, I will show you if I am having the photograph of how it looks like in the field. This is back tilted. Okay. So, usually what happens that if you are having like you have a flat you can say the surface, and then there is an faulting here, reverse fault, you can say it is not reverse exactly, but mostly we see thrust fault. Then if there is a movement here, then the landform will be developing something like this. Okay. So, there is an uplift over here, and then there is a back tilt we say, because usually we see that in such areas the slope will be in this direction, but the slope here is in the opposite direction. That is the reason why we call this a back tilt. Okay. So, mountain front sinuosity, it is the sinuosity of topography of the mountain fronts. Mountain fronts are defined as topographic escarpment bounded by major faults. It is an index of degree of irregularity. That what I was talking about, that if you are having the sinus, that is the degree of irregularity if you take this as an whether it is straight or not. Okay. The degree of sinuosity of this fronts provide an authentic and dependable evidence of active tectonism in arid and semi-arid areas. If it is in the humid region or where the system is very dynamic, that is fluvial system, then you may see more of erosion, more of dissection there. Okay. So, mountain front sinuosity is denoted as S is the ratio of the observed length along the margin of the topographic mountain front, that is the Piedmont junction, and LMF to that is the ratio between S is equal to LMF that and LS. Okay. So, this is how it has been given. S is equal to the LMF by LS. LS is over the straight line. Okay. So, this we will see quickly. So, and then we will end here. Okay. So, suppose this is the straight length you are having, and this one is the mountain front. Okay. And that has been denoted as S is equal to LMF by LS. So, I will stop here and we will continue in the next lecture. Okay. Thank you so much.